Hello everyone, my name is Chaitanya and I am from Team Arthur. My teammates are Babar and Farhat. We are going to give a presentation on B-spline curves and surfaces. Here are our team members' contributions. I am going to explain the topics B-spline curves, curve point evaluation algorithm, affine invariance, strong convex hull property, local scheme, piecewise polynomials, piecewise linear approximation. And Babar is going to explain various continuities, derivatives of a curve, higher derivatives, derivatives with respect to a knot. And Farhat is going to explain on the topics B-spline surfaces, bivariate basis functions, surface derivatives, derivative surface, design examples, and GMLab. Let's get into the part 1 technical details of the topic. B-spline curves. A spline is a curve that connects two or more specific points, or that is defined by two or more points. Means each control point will affect the shape of a curve or a range of parameters. The use of B-splines to define curves and surfaces for computer-aided geometric design was first proposed by Gordon and Reisenfeld. Here we have a example diagram of how a B-spline curve looks like. B-spline curve definition. A pth degree B-spline curve is defined by C of u equals to summation of I from 0 to n of u into p of I, where p of I are the control points and n of u is the pth degree B-spline basis function defined on non-periodic and non-uniform knot vector. The knot, we have a knot vectors from x of u and u2, u3 and so on till un, and further we have the control points, n plus 1 control points. The order of the curve is p. Here for the following example we have the knot values x0, x1, x2 and x3, and the control points for this are p0, p1, p2, p3, p4 and p5 and p6. This curve is made up of n minus p plus 2 segments. Basis functions. We have the following formula for the basis function, and here we have three cases for taking the value of ti. When I is less than k, the ti value will be taken as 0, and when I is lies in between k and n, then ti value is substituted as I minus k plus 1, and if I is greater than n, then we take ti as n minus k plus 2, as we have seen from the before slide, meaning n of u equals to 1 if u lies between ti and ti plus 1, and it is equal to 0 otherwise. Here are some examples of basis functions. Here is a cubic basis function on u for the following parameters, and here below we have a cubic curve then on using the above basis functions. Curve point evaluation algorithm. We have the pseudocode here for the curve point. Here we will be taking the inputs as small n, small p, capital U, capital P and small u, and the output as C. It will be computing the curve point C using the curve point function, taking the inputs n, p, capital U, capital P, small u and C as parameters. We'll be finding the span using the find span function of find span by using find span of n, p, u and capital U, and we use the span in the basis function by substituting on the basis function of span u, p, capital U and n. We'll be initiating C as 0 and we'll run a simple for loop by which we compute the value of C by C equals to C plus n of I multiplied to P of span minus P plus I. In summary, to design a B-spline curve, we need a set of control points, a set of nodes, and a degree of curve, as we can see from the pseudocode above. Here is a cubic B-spline curve on the following parameters. Here in this example, this is a cubic Bezier curve. Affine invariance. Affine invariance is an affine transformation is applied to the curve by applying it to the control points. Let us assume R be a point in Euclidean space E power 3, that is a three-dimensional Euclidean space. So here an affine transformation is denoted by phi, which maps E power 3, that is Euclidean space, into an Euclidean space and has the form phi of R equals to AR plus V, where A is a 3 by 3 matrix and V is a vector, and also A of R will be a 3 by 3 matrix. Affine transformations include translations, rotations, scalings and shears. The affine invariance property for B-spline curves follows from the partition of unity property of the n of u. Thus, we'll let R equals to summation of alpha I pi, where p of I belongs to the Euclidean space, three-dimensional Euclidean space, and summation of alpha I equals to 1. Now for phi of R, we'll be substituting the before formulas and we'll be computing the following equation. Phi will be getting phi of summation of alpha I pi in place of R, which equals to A summation of alpha I pi plus V, and further by computing we get summation of alpha I API plus summation of alpha IV, which is equals to summation of alpha I API plus V, and further by substituting we get summation of alpha I phi pi, which is equals to phi of R. So finally we get phi of R equals to summation of alpha I phi of pi. Strong convex hull property. The curve is contained in the convex hull of its control polygon. If U is in the node span Ui and Ui plus 1, where I is in between P and M minus P minus 1, then C of U is the convex hull of the control points Pi minus P, so on till pi. Here in the example figure, the blue line with the curved edges is a Bezier curve, and the black lines with sharp edges is a convex hull containing the Bezier curve. Here is an example of strong convex hull property for a quadratic B-spline curve. Here U is belong to in this we have elements of U as U3 and U4. So by the strong convex hull property, we have C of U as P, is a triangle which is in between the points, control points Pi minus 2, Pi minus 1 and Pi. Here in this diagram, P1, P2 and P3 is a strong convex hull property of the quadratic B-spline curve. Here we have another example of strong convex hull property for a cubic B-spline curve. Here U is defined between points U4 and U5, hence the convex hull is extended to the points Pi minus 3, Pi minus 2, Pi minus 1 and Pi. So the strong convex hull here is a quadrilateral, C of U is a quadrilateral, that is of the points P1, P2, P3 and P4. Local scheme. A single span of a B-spline curve is controlled by k control points, and any control point affects k spans. Changing the position of any control point Pi only changes the curve P of U on interval Ui and Ui plus P plus 1. Here are examples where U is not in the interval. Then n of U Pi has no effect in computing of P of U. And in here, so suppose U is in the interval and n of U is non-zero. If P of I changes its position, then n of U Pi is changed and consequently P of U is changed. Here we have some examples of this local scheme. First, we'll look at the quadratic B-spline curve, which is defined on U for the following parameters. Here the curve, we can see that for this quadratic B-spline curve, the curve is a straight line between C2 by 5 and C3 by 5. And in the next example, we can see a cubic curve which is defined on U for the following parameters. Here we can see when we move the control point P4 from P4 to P'4, this changes the curve, the shape of the curve in the interval 1 by 4 to 1. Piecewise polynomials. Piecewise polynomial function is a function that is a polynomial on each of its subdomains. Let us look at Bezier versus B-spline curves. There are many similar properties from Bezier and B-spline curves, but there is a main difference between them. Let us first start with the Bezier curves. A parametric curve of the form, a Bezier curve is a parametric curve of the form Ct equals to xt comma yt, where xt and yt each are real valued polynomials of some degree d greater than 0. Where we have xt equals to sum of xi bi of t and yt equal to sum of yt multiplied by bi of t, where bit are Bernstein polynomials and xi yi are real numbers. Let us go and talk about the B-spline curves now. Same as the Bezier curve, B-spline curve is a parametric curve of the form ct equals to xt comma yt, but here we have xt and yt are real valued piecewise polynomials and of some degree t greater than 0. Here similarly we have xt equals to sum of xi bi of t, xi into bi of t, and yt equals to sum of yi multiplied by bi of t, where bit are B-spline basis functions and xi and yi are real numbers. Let us look at a quick demonstration of difference between a Bezier curve and a B-spline curve. This is an example of a cubic Bezier curve, and here we have the following as a control points, and the shape of the curve is controlled by the control points. Here we can see as the control point moves, as the parametric value moves, we can see the control points become more stronger. That means as we move the control points, the shape of the curve will be changing. With each change in the control point, the shape of the curve will be changing. Let us look at B-spline curve. Here is a B-spline curve, and let us look how a B-spline curve works. Here also we have a control points which are in this color, and we have the B-spline curve traversing through the control points, and when we move the control points, when we change the position of the control points, the only the particular section of the curve, B-spline curve, will be changing. Let me show you. When I change the control point, only the particular section of the B-spline curve is changing based on the change in the position of the control point, but not the entire B-spline curve. This is why, as we have studied earlier, we can see the change in any control point only changes the curve in the section of in a particular segment. Piecewise linear approximation. The control polygon represents a piecewise linear approximation to the curve. This approximation is improved by knot insertion or degree elevation. As a general rule, the lower the degree, the closer a B-spline curve follows its control polygon. Here we have two examples. The first one is a 9th degree Bezier curve on the knot vector u for the following parameters, and we can see how the Bezier curve is traversing through the control points. In the second example, we have a quadratic curve using the same control polygon but it is defined on U for the following parameters. We can see how the curve has changed its position based on the degree of the curve. Let us look at this example to get a better idea. For the curves of the figure are defining using the same 6 control points and the knot vectors, but the B-spline curves have the different degree but have the same control polygon. You can see how the change in degree is changing the shape of the B-spline curve. That is, the lower the degree, the closer the curve is going to the control polygon, as we have studied earlier. So as the degree increases, the curve is moving away from the control polygon.
Hi. So a continuity is when two curves are joined. So in this figure we can see there are 4 types of continuity which we will discuss. C raised to power minus 1 means that the curves do not join, while the C raised to power 0 means they are at the same point when they join, and C raised to power 1 means that the curve share the same parametric derivatives when they join. C raised to power 2 means that the curve share the same second parametric derivative when they join. So in this image, this image is drawn on these quadratic values of u, as you can see, and in this image, in the above one, C1 and C2 continuities are being used, and the values of P4, P5 and P6 are collinear, while in the second image, which is a quadratic curve, the first derivative C0 and C2 continuities are being used, and which means that C1 is continuous at u is equals to 4 over 5, and this discontinuous function can sometimes also show in such a way, can sometimes combine such a way that the result will look continuous. So in this image there's a quadratic curve, and which is drawn on the on these values of u, and this image has a double control point, which means that P2 is equals to P3, and which means that it has a continuity on C raised to power 0 and C raised to power 2, and the node u is equals to 1 over 2 has multiplicity 1, and which means the curve is continuous, and the magnitude of first derivative vector going to 0 is at the value of u is equals to 1 over 2. So now to calculate the derivative of curve, we have this formula, which is equals to Cu is equals to summation of I up to n into I into P into U into Pi. So after opening up and taking the derivative, we get this value, and after doing these multiple calculations, and we get the final value, which is this one, which is I up to n 0 into n minus 1, n into sub of I plus 1 into P minus 1, U into Qi, and where the value of Qi is this one, as you can see. This is a pseudocode algorithm for computing the derivative of B-spline curves. In this one, n denotes the number of control points, which is n plus 1, p denotes the degree of the curve, and u denotes the nodes, and p also denotes the control points. So in this one, we use a for loop and initialize ck to 0, and after that we call the derivative basis function, which has parameter of span u and ds, and we again use the for loop, and our final output array is this one, ck, where ck is the kth derivative from in which the value of k is greater than 0 but less than t. Although B-spline curves are more complicated than Bezier curve, but The derivatives share a very similar format. So let CKU denotes the kth derivative of CU, and if CU is fixed, we can obtain CKU by computing the kth derivative of basis function. This can be used to compute the kth derivative of the B-spline curve. So now instead of fixing u, we want to formally differentiate the PS degree of B-spline curves and define a node vector. In this case, the value of u on 0 will be p plus 1, and on 1 it will be also p plus 1. So applying this equation and this equation together, we get this result, which gets up to C naught is equals to summation of I 0 up to n I naught into of p into u into pi. Now to calculate the value of u naught when the value of the u0 is equals to the control point is equals to only p, we can also calculate it using the same way as we calculated it for u plus p plus 1 with the derivation of the basis function, which is this equation. So the final value we get is this one. In this case, I is equals to up to n minus 1, while the rest is n sub of I plus 1 into p minus 1 into u into qy, where the value of qy is given this one. This will be an example of quadratic curve defined on B-spline curve defined when it has a degree value of 2, and this will be defined on these node values of u, and we can see we will get the cu is equals to I up to summation of 3 and I into 1 into u into qy, and this will be all the values of 4 values which will be calculated, because I is up till 4, so we'll have 4 values. And from the previous equations we know how to calculate the value of q, so we will just plug in the numbers and this will the 4 values we will get. So as we can see, the value of q naught lies between 5 and between p1 and p naught, and value of q1 lies between 10 by 3 between p2 and p1, and the value of q2 lies between 10 by 3 into p3 and p2, and the value of q3 lies between p4 and p3. And after removing, we get this polygon shape, and which we can see all the quadratic values of the four knots which we are looking for when we have degree is equals to 2. In this example, we have a degree of 3, so we define our cu is equal to I up to 6 and I of 3u into pi, and the cubic curve will be defined on these terms. And after derivation, in the u naught we will remove the first and last values, and the new cubic new equation will be 0 up till 5, and we will have 6 values of q, which can be calculated by plugging in the values in the equation of q. And in this figure we can see the result of the 6 values that we plugged in, and the value of, for example, q naught will lie between p1 and 9 of p1 and p naught. So q1 will lie around this area, and the value of q2 will be 9 over 2 between p3 and p2, and this is the polygon figure which we will get of all the 6 values of q. Since the first derivative of B-spline curves is another B-spline curve, so recursively applying this equation on a B-spline curve and a basis function, we can generate the higher derivative. So recursively applying the derivatives on this equation, on these two equations, can generate higher derivatives of B-spline curves, which is this value. So in this figure, in the top one, we can see a quadratic curve with of higher derivative B-spline curve with the vector value of c20 and c21, and in this one c2u is a piecewise 0 degree curve. And in this second figure we can see the derivative values of up to c raised to power 3. So this is a prime example of high derivatives, and high derivatives are much more commonly used in B-spline curves than the quadratic or cubic derivatives. For calculating derivatives with respect to a node, we use divided differentially on the basis function. After that, we get this equation. And in this one, for a curve, it has to be a right derivative, where uk is a node of multiplicity. For a curve with respect to a node, we use this function, and the definition of right derivative depends on following values. If I is equals to 0, is equals to k minus p to minus 2, it is equals to, the derivative will be equal to 0. If I is equals to k minus p minus 1, it will be equal to this function. And if I is equals to k minus p up to k minus 1, it is equals to this function. Also, we must keep in mind that the derivative of right and left are very similar. Thank you.
Surface. It's an extending idea of B-spline curve. It constitutes of three elements: a bidirectional net of control points, two knot vectors, and the product of the univariate B-spline function. Here is the equation where these are three elements. So we can define the B-spline surface with two knot vector u and v as the summation over I0 to n, j0 to m, nip of u into njq of v into pij. To compute a point on a B-spline surface, we have some steps. The first step is to find the knot span in which u lies. Say u belongs to in the range from ui to ui plus 1. Then compute the non-zero basis functions. Then again find the knot span in which v lies, and again the v belongs to the range from vj to vj plus 1. Then also compute the non-zero basis function nj minus q of v to the last nj comma q of v. And the last step is to multiply the values of the non-zero basis functions with the corresponding control points. Here is an example where we can see this is a B-spline surface. It's a 6 column and 7 rows, and these are the knot vectors in u and v direction with their degrees. For example, let p is equals to q is equals to 2, and the summation over I0 to 4, j0 to 5, there is a multiplication with these two vectors to compute s with the knot vector 1 by 5, 3 by 5, where 1 by 5 belongs to from this range u2 to u3, and 3 by 5 belongs to the range from v4 to v5. We can get this equation. Then bivariate basis functions. It has some properties like non-negativity, partition of unity, local support, differentiability, maximum value, and these are some example pictures of basis functions we are going to talk about. At first, the non-negativity, the multiplication of nip of u into njp of v will be always greater than 0 or equal for all value of I, j, p, q, u, v. Then the partition of unity, we can see from the equation here that the summation over I0 to n, j0 to m, nip of u into njq of v will be 1 always for all knot vectors belong to this area. And then the same multiplication will be 0 if the knot vector is outside this rectangle, the following rectangle. The next property is local support. Local support, actually the multiplication of these two elements is non-zero in this area, following area, And the continuity and differentiability of SUV is close to the basis function actually, especially this surface is p minus k into q minus k times differentiable in the direction of u of v at u of v naught, which is of multiplicity k. Then if p is greater than 0 and q is greater than 0, then nip of u into njp of v gets exactly one maximum value. Then we come to the surface properties. We will discuss here some properties like generalization of Bezier, endpoint interpolation, affine invariance, a strong convex hull property, control net forms approximation, single control points affect the surface locally, and the last is surface is continuously differentiable. These are some example pictures of B-spline surface. At first, we will discuss the generalization of Bezier. Bezier curves are the fundamental importance for computer-aided geometric design, in short CAGD, and also it's used for curve design, and it's actually the starting point for several generalization, which to higher dimension and also to B-splines. And Bezier curves with n dimension is defined as follows in this equation, where the t the range of the t is from 0 to 1. And the next, the Bezier polynomials generalized, which are formed according to this definition, which have some properties like affine invariance, symmetry, and endpoint interpolation. And also, in addition to generalized Bezier polynomials, for a straight control polygons are again straight. Next, we will discuss endpoint interpolation. In Bezier, curves passes through B0 and Bn, which verify using scheme for T0 is and 1. But unlike Bezier, B-spline had no endpoint interpolation. Then affine invariance. Linear interpolation is affinely invariant, and under affine parameter transforms beyond 0 in the range 0 to 1 to A to B, we can get this equation. And also an affine invariance is actually an affine transformation, which is applied to the surface by applying to the control points. So we can see in the following equation. Then it's an important property, surface property, which is strong convex hull property. Curve stays within convex hull of control polygon, and if this knot vector is belongs to this region, then the surface is in the convex hull, and the control points Pij as the I and j are defined as following equations. And also it follows non-negativity, partition of unity, and also in any given this rectangle, the at most p plus 1 into q plus 1 basis functions are non-zero, especially in the particular the multiplication for this range of I and j. And for example, if we want to see same B-spline surfaces, but using different degrees, we can see some differences here. If triangulated, the control net forms a piecewise linear approximation actually to the surface, and the lower degree between the approximation, as you can see in these figures. Here you can see the left one is quadratic and the right one is biquadratic surface, where the p is equals to q is equals to 4, but the left one has p is equals to q is equals to 2. Next, we will discuss the impact of control point movement. You can see this initial surface is flat, control lie in a common place. The control net is actually offset from the surface for better visualization. But if we move a point P35 is moved, it affects actually the shapes only in the rectangle where it lies actually. So other rectangle is in the flat surface, but this point moved the only affected rectangle. Then we will discuss the isoparametric curves. The surface, B-spline surfaces are obtained in a manner analogous to the Bezier surface, and if we manipulate the normal B-spline surface curve, we get the equation where we can see it's an isocurve of B-spline surface. CU naught is a cube degree B-spline curve on V, and CV naught U is a path actually B-spline curve on U. The point is U naught comma V is at the intersection CU naught of V and CV naught of U. All lengths are shown on the surface are actually isolines. So for example, we can see a curve, isoparametric curve picture here. If we think about a rectangle and but just keep constant one value and changing another value, it creates a isoparametric curve here. Suppose we keep constant U is equals to 0.4 and change the V from 0 to 1, it will create the one surface. So and vice versa. So surfaces with plane discontinuities, you can see from these two pictures, the left one is quadratic x cubic surface with crease with these two knot vectors, and the right one is bicubic surface with crease with these two vectors, but P2 j is equals to P3, j is equals to P4, where j is from the range from 0 to 4 and equal. Let's discuss them individually. At first, this picture, the crease in the surface corresponding to the knot line where U is equals to half. It's possible to position the control points in such a way that they cancel the discontinuities in the basis function by using multiply coincident and control points, and visual discontinuities can be also created where there are no corresponding discontinuities in basis functions. Then the next picture with a surface which is bicubic with no multiple knots, and the second partial derivatives are everywhere continuous. The crease is due to the multiple control points. Then we came to the surface derivatives. If we manipulate, differentiate the common equation of B-spline surface with the respect of U and V, we get those equations. And in the right side, you can see the direction of the derivatives of a surface, B-spline surface. And this is the pseudocode algorithm to get the surface derivatives, where in the first lines we compute the du and dv, and then in the last for loop it calculates the actual surface derivatives, and it the full function get the input, take the input of n p u m q v p u v d skl. Then we will discuss the recursive formula with control point differential. This is a bicubic surface defined on these two same knot vectors, and if we manipulate the common equation of B-spline surface, at first if we differentiate it in the respect of u, we get the left one equation, and if we differentiate it in the respect of v, we get the right equation. If we take both into account, we will get this final equation with respect of both u and v. So let's come to our part 2, which is design examples. You can see this is a can where in the top and also in the body you can see some surfaces. Also this is a goat where it has also so many surfaces. Here you can see in the head, in the body, and also leg, in the brain, it has surfaces. and it's here is the airplane, toy plane actually, and it's also have some surface curves in his body. Let's come to the part 3, GM lab, where I will show you the example using the Autodesk Maya 2020 version of B-spline surf and curve. You can see the example of a goat here. The link is given in the slide. You can also visualize this, and if you just zoom there, you can see there are many surfaces here in the body, in its body. And also if you can choose the any surface here. Let's and also any type of surface you can choose, and if you move, it just affects the shape here actually. So you can just edit as what you want to choose here, and yeah, you can see the shape is changed, and there are also so many surfaces in its body, and after adding all the surface, it creates the whole goat model.